Hello everyone, I am Wang Chaiming from Beijing Institute of Technology, China. I will introduce our paper NameChecker, detecting inconsistency between method names and method bodies.
This is my outline. The first part is the problem. Identifiers play an important role in program comprehension and software maintenance. It is reported that about 70% of the source code is identifiers. It includes different types such as class names, the method name, the field name, and the variable name, and etc. Um, and this picture shows some examples of identifiers. As an important type of identifier, concise and meaningful method names can provide intuitive information on the behaviors of the name methods. Method names are not only the interface for transferring information between functions, it is also a summary description of the long and complex method body. And a high-quality method name has many benefits, such as it can improve the readability of our code, help developers understand functions faster, and help code understanding and project maintenance. However, developers often write inconsistent method names due to different reasons. For example, the improper code cloning or in the software maintenance process, the method body was changed but the method name was not modified simultaneously. And inconsistent method names can lead to serious consequences, for example, making the function of the methods difficult to understand, misleading the use of method APIs, and even leading to software defects. This is the real example taken from an open source project Maven Surefire. The first line indicates that the method was named getFileOutputStream in the initial version, and the second line indicates that the method name was changed to getFileWriter in a renaming operation, and the method body kept unchanged. We can find that the function of this method is to return the writer corresponding to the file instead of output stream, so getFileOutputStream is an inconsistent method name. Notably, manual validation of the inconsistent method name is often time-consuming, and so to this end, automated validation of the inconsistent method name is highly desirable, and a few tools like the approach proposed by Liu and MNIRE have been proposed recently to automatically identify inconsistent method names. In order to identify inconsistent method names, they first parse a method into two parts, the method name and the method context. The context includes method body and the other information like the type of parameters or return values. Then they recommend a new method name based on the method context, leveraging neural network, and then they compare the new method name with the original method name to check whether this method name is consistent with its associated method body. This is the result of the existing technique. Evaluated on the same test dataset, which contains 2,700 methods. The performance of these two technologies is shown below. As we can see, the performance is good. However, there is still room for improvements because the accuracy is only about 70%. And in this paper, we proposed a more efficient approach to deal with the problem of automated identification of inconsistent method names. And the second part is the solution. This is the overview of our approach. We reuse the repositories collected by Liu, and we first mine the commit history of the code repositories for the renaming operations, and then we obtain the inconsistent method names and consistent method names and keep the ratio of them balanced. Then we perform feature extraction on the obtained methods. And next, we divide the dataset and the collected methods into training data and testing data. The training data is used to train a binary classifier. Then we use this trained classifier to evaluate each method in the testing data. Here we present the dataset construction. We first traverse every two adjacent commit versions to find the changed methods between these two versions, and then we use mining rules to obtain consistent and inconsistent methods. We consider the method name of the previous version, which is the buggy version before renaming, as an inconsistent method name, and the later version, which is the fixed version after renaming, as a consistent method name. We also extract the context information of the current method for subsequent use. We extract four features from the implementation of the method. The first is the identifiers in method body. We extract all lexical identifiers that appear in the method body. And the second one is input and outputs. It means the input parameters and return type of the method. The third is the return value. It mainly represents the return information of the method. This includes the field access method invocation in each return statement. And the final one is the abstract statements in method body. This is actually the node type in abstract syntactic tree. This is an example of four features as far as this method is concerned. The feature identifiers in method body is just two method invocations in method body, and the input and outputs is volume manager, which is the return type of this method, and the feature return value is just get volume manager, and the last one is just the node type of the statement in abstract syntactic tree, which is return statement. This is the structure of our classifier model. It is mainly divided into three parts. In the first part, we take the four features and their method names as input, and then pass them into vectors with the help of embedding techniques. And the embeddings are fed into the subsequent network. And then in the second part, we design different networks to process different features. We use two-layer LSTM to process method name, and we use LSTM and attention to process identifiers in the method body. And we use fully connected layer to process other features. Finally, we get the vector representation of each feature respectively. And then in the third part, we use the attention mechanism to process the above 5 encoding representations, and finally get an output in the range of 0 to 1, where 1 indicates that the method name is inconsistent. The third part is evaluation. Regarding the dataset, we reused the high-quality projects collected by Liu, and these repositories come from 4 well-known organizations, and the details are shown in the table. Now the Apache, the Spring, the Google, Hibernate, and these 4 well-known organizations. And through mining these repositories, a total of 39,000 inconsistent method names is obtained, and the same number of consistent method names and contexts were obtained. These are our data processing. Firstly, we use Java parser to parse source code for feature extraction, and then, according to the camel case and underscore word segmentation, we get the token sequence of each feature. And notably, we convert all the tokens into its lowercase. For example, the get file writer will be parsed into like that this way. And then we set the threshold for truncation and completion to adapt to the neural network input. And this is our model parameter. We have three research questions. The first research question: does NameChecker outperform the state-of-the-art approach in identifying inconsistent method names? And we compare the NameChecker against the state-of-the-art approaches. The approach proposed by Liu and MNIRE. The two approaches are selected because they represent the state-of-the-art and their performance is the best. This picture is the performance of identifying inconsistent names. We can find that NameChecker outperforms the other two approaches in precision and F1 score, but it is relatively lower on the recall indicator. We found that the approach proposed by Liu and MNIRE identify most of the test methods as inconsistent, resulting in a high recall reaching more than 95% and a low precision which is around 50%. And this picture is about the performance of identifying consistent method name. We can find that the NameChecker outperformed the other two methods in precision, recall, and F1 score, because too much test methods identified into inconsistent by the other two approach. So the recall of identifying consistent method name is extremely low. In a comprehensive comparison, the performance of NameChecker is better than the state-of-the-art. And the second research question: how does each feature contribute to the effectiveness of NameChecker? This research question concerns the effect of the employed features. NameChecker uses 4 types of features to quantitatively investigate the effect of such features. We disabled one of them at a time. The result is as shown in the table. As we can see, the feature identified in the method body has the greatest impact on NameChecker, while the feature abstract statements in method body feature has the less impact on NameChecker. The third research question: how long does it take to train the neural network-based classifier, and how long does it take to make predictions? And we can see that in model training, NameChecker needs 30 minutes, but MNIRE needs 3 hours. In model predicting, NameChecker predicts over 1,000 methods in 1 second. And now we jump to the conclusion. First, natural language processing technology is effective in the detection of inconsistent method names. And second, the improvement brought by the recommended technology is limited. And third, the text information and structure information are necessary, while the text information is more important. Yeah, that's all.